Hi everyone. Let's talk about definite integrals. We are given 4 approximations for the area of the region under the graph of the function x squared from x equal to 0 to x equal to 3. Can we use these approximations to determine the exact area of the region under the graph of this function between 0 and 3? To make things easier for us, I already computed the total area of all rectangles in each picture. Because the rectangles fit the region better and better, the numbers approximate the area of the region under the graph of this function better and better. The numbers are 11.38, 10.16, 9.69, 9.34. I could obtain more approximations if I used more pictures that use more rectangles. If I did so, I would create a sequence of better and better approximations. What do you think the limit of this sequence is? If I were going to guess it, I would say it must be around 9. I don't know exactly what it is. It could be 905, could be 903. It's also possible that the limit does not exist. However, if I was going to guess, I would say that the limit of this sequence is 9, which suggests that the area of the region under the graph of this function between x equal to 0 and x equal to 3 is exactly 9. Is there a way to confirm this answer algebraically? In other words, is there a way for me not to guess the answer, but to compute the answer? This is where definite integrals come into play. Imagine you want to find the area of the region under the graph of the function f of x between a and b. We will generalize the method from above that used rectangles. To generalize it, we will use n rectangles, where n represents any positive integer. The first thing we do is we take the interval from a to b and we split it into n subintervals of equal length. Let me do this here. I have an interval from a to b. I will split it into n subintervals of equal length. Let me give names to those points that split my interval into subintervals. I will call a by a new name, x0. The next point will be called x1. The next point will be called x2, and so on. The last point, which in our case is b, will be called xn. The point before that will be called xn-1. All these subintervals have the same length. Let's give a name to this length. I will call it by delta x. If you know what a and b are, you can easily compute delta x. Delta x is the length of one subinterval. The length from a to b is b minus a, and you have n subintervals, which means the length of one subinterval is this length, which is b minus a, divided by the number of rectangles or the number of subintervals, which is n. These subintervals will serve as bases of our approximating rectangles. How should we determine the heights of the approximating rectangles? We will choose what we call a sample point in each subinterval. In the first subinterval, I can choose any sample point I wish. For example, I can choose this one. Let me give a name to this point. I will call it x1 with a star at the top. In the second subinterval, again, I can choose any point I wish as my sample point. Let me choose this one. I will call it x2 star. In general, in the ith subinterval, I will choose a sample point that I will call xi star. These inputs, these sample points, will determine the height of my rectangles. For example, the height of the first approximating rectangle will be the value of the function at x1 star. The second approximating rectangle will have the height equal to f of x2 star, and so on. The picture on the right side shows the result of our partition. Take a look. The first rectangle has the height equal to the value of the function at the first sample point. The second rectangle has the height equal to the value of the function at the second sample point, all the way to the nth rectangle, which has the height equal to the value of the function at the nth sample point. What is the area of all of these rectangles? Let us compute it. We can compute the area of the first rectangle by multiplying its height by its length. The height of the first rectangle is given by the value of the function at the first sample point. The width of the first rectangle is delta x. Now, to compute the area of the second rectangle, we multiply its height, which is given by the value of the function at the second sample point, multiplied by its width. And I would continue this computation. I would do f of x 3 star times delta x and so on. This pattern continues until I reach the last rectangle. The height of the last rectangle is f of x n star times delta x. This is exactly the area of all of the rectangles you see on the right side. This is a long computation involving many terms. Thankfully, these terms are very similar. Note that the only difference between the first term and the second term is the number right next to x. That number changes from 1 to 2. The next term would change 2 to 3. Similarly, the last term, the only difference between the first term and the last term is the number in the subscript of x. Mathematicians found a way to write this sum in a shorter way. They use what we call sigma notation. They use this Greek letter sigma, which means the sum. Because these numbers that are changing go 1, 2, 3, 4 all the way to n, they say that the sum starts at I equal to 1 and ends at n. The first number is 1, then it's 2, then it's 3, all the way up to n. This is exactly what this notation means. You start at 1, then you will go to 2, you will go to 3, all the way up to n. The terms that you are adding are of the form f of xi star times delta x. Note that when I is 1, this I changes into 1 and you get exactly the first term. When I changes into 2, you will get exactly the second term. Then you get the third term, fourth term, all the way up to the nth term. And nth term is the last one that you use. This notation means exactly the same thing as this. In other words, this expression, which is the same thing as this expression, represents the sum of all of these rectangles. We want to get better and better approximations, which means we want to have more and more rectangles. In other words, we want this number n to go to infinity, which means we want to take the limit of this expression as n goes to infinity. Because this expression can be written in a shorter way, this way, what I want to compute is the limit as n goes to infinity of this expression. What I'm trying to compute to get the exact area of this region is the limit as n goes to infinity of this sum from I equals 1 to n of f of xi star delta x. This limit gives you the exact area of the region under the function f of x between a and b. This is a lot of writing. You have to write the limit of the sum of certain terms. Instead of writing this expression, mathematicians often write the following: the integral from a to b of f of x dx. When a mathematician writes this, they mean this. The expression on the right side is called a definite integral of f of x between a and b. And the meaning of this expression is the area under the graph of the function f of x between a and b. We compute it by computing the limit of this sum. I have one more remark about definite integrals. The notation of a definite integral reminds you what the definite integral represents. Remember, delta x represented the length of one subinterval. As you get more and more rectangles, these subintervals get smaller and smaller. Mathematicians often denote very small delta x by dx. This expression, f of x dx, reminds me that while computing areas under graphs of functions, I multiply the height of each rectangle, given by the value of the function at the sample point, by the width of each rectangle. This expression, f of x dx, reminds me of the area of one approximating rectangle. The integral tells me to add all such areas between a and b. This table says everything we just explained. If you would like to stop the video now and read it carefully yourself to make sure that you understand it, that would be a good idea. In the next video, I will show you how you can use this limit definition of the definite integral to compute a definite integral.